This
It could
is a picture of the blades.
eat out to destroy pinion fan blade.
So these blades generally aren't too difficult to replace, and it's, you know, if you're an airline mechanic, almost everybody gets a chance to replace them. They get a ding big enough, it's replaced, and they're balanced. So there used to be a whole process where we put a blade as closely matched, and we'd have to balance, and it was kind of a lengthy process, but we figured out a quicker and easier way to do that. Is if number 9 blade there were damaged, we would replace number 9 and the blade completely opposite of it. So when we would take those blades out and we would get a new set of blades, and they were exactly the same weight. So we put them in, and the airplane would maintain its balance. Both of those blades would go back, the one would be repaired, and the non-damaged blade would be inspected and matched with another with equal weight.
What's the diameter of the outside tip?
The blade, this blade is probably close to 18 inches from edge to edge. And is that what you're asking?
I'm actually, because
The thickness in the
concerned
back.
because obviously the issue with propellers is that once you can't have the tip go past the speed of sound, it would seem like that at 3,000 RPM that the tips would be going past the speed of sound.
What's the speed of sound?
Well, it's going to vary. It's about 600 miles an hour, but it varies. It obviously changes with altitude. You see.
You ask a good question. It never really occurred to me. It can't exceed. Oh, because you'd get sonic.
Yeah, you're going to get the.
Yeah. And I'm assuming it would be safe to assume that it doesn't exceed
doesn't.
the speed of sound.
It just looks like a massively large diameter, and at 3,000 RPM, it seems like it would just be over that.
You can see a little bit of a white area in here. This in here is the engine inlet. This is your compressor, your first stage compressor back here. And then the outside from there on is what we call a cold airstream. This is a propeller engine. It literally is a propeller engine. This we call this the N1, or the first stage. I guess this would be second stage this isn't a compressor. This is our N1 blade.
That's what they mean by high bypass.
Yeah, high bypass, because most of your flow through here goes through this cold airstream. And the cone on here, this is an incomplete cone. They do design these cones as best they can, that if material is carried in towards the center here, the cone is supposed to deflect it past the engine inlet and direct it into the cold airstream to keep it out, because it destroy that engine. If they can get it into the cold airstream, it's going to do very little damage, maybe to a blade, but it'll be flying within hours. But if it gets into that compressor, then you're talking millions of dollars repairs.
The majority of your thrust comes from this high.
Yep, the high bypass, the cold airstream. This engine out here does not have a cold, it's not a high bypass. It doesn't have a cold airstream. In fact, I saw it. I just ran across it. There's a picture of me at TWA way up in the cold airstream. Look at the back of the engine. If I see it, I'll bring it in. Okay, so I don't know if we did this one or not. I don't think so, because my last numbers are 97. This isn't too tough. Yellow, violet, orange. So it's 4, 7. Yeah, we did that one. Okay, this one is a more you're not going to see too many of these. So this one's a little bit different. If you remember, when we have 4 colored stripes, the first 3 are digits, and that's going to be our multiplier here. And then this one, I think that's red. Oh, or it's actually, I've got violet. So it's going to be plus or minus 7%. I'll show you on the graph. I think it's coming. You've got it in your book. So this, I've got red, black, black, brown. So it's going to be when it's got 4 colors, the first 3 are digits. So it's going to be 200, 200, And then the multiplier is brown, which is 1, another 0, so 2,000. You could do a 2,000 with fewer stripes, obviously, but you still get the same value. This is but this is what they call a precision resistor. So the violet is 7. It's going to be plus or minus 7%.
1860.
14.
So when you look at the tolerances here, that we had 4 colored stripes. If you notice, these line up. Brown is 1. Matching our color code. 1%. 2, red is 2, 2%. Orange 3, 3%. Yellow 4, 4%. Green. We get, actually, my error. That's 0.1. Did I have that in there? I didn't even follow through with it. So I was wrong. Yes.
For that image you just showed us, in the book it shows there's a resistance for gray and white, but on that sheet it showed none.
For
The picture you just had up, that one right there, gray
yours
and
is
white.
different.
Yeah, we have a tolerance, and there's no tolerance on this one.
Okay. This one, I can't. This is probably material that was given to me, maybe a little older.
Okay.
You may have a revision. And I was wrong when I said that was 7%. It's 0.1. You've got, what are your values for gray and white?
Wait, no,
8 and 9.
8, 9.
They all go the same.
yeah, we still have
Yeah,
7%.
And they're not okay. The point I'm making is, as long as you go, and that's how I made a mistake on that last one with the 7% with violet. The ones, you'll only be tested on this once or twice during the course, so it's not going to make or break you. As long as all the examples we use in this class, it will be whole numbers. So you won't get a green or a blue or a violet. You'll get a brown, red, an orange. One of these where the number is the same percentage. You're not likely to get involved with resistors. The FAA wants you to understand resistors. There may be times when you have to go in and identify a certain configuration of who knows what. Resistors can be a lot of different components. If you are getting into color codes like this, the only way I can see that happening is if you're called into a shop. If you guys were all hired, if this was the class and I was the airline and you were all my new hires, eventually I'm going to find out what all your skills are. And if you've got higher skills, I may put you in a shop where you might be doing modifications to equipment. Usually that stuff is sent out. But there are times when we'll get a package and we can do modifications in our shops if it saves us a lot of money. And if that were the case where you're removing resistors and replacing resistors, it's going to be 3rd grade level. You're going to have pictures, you're going to have a color code, you're going to have step-by-step instructions. It's going to tell you the value of the resistor, and it's going to tell you in the text the resistor colors you should be looking at. So there's no mistakes. Shops can be great. If you slide shop, that was one of the most cush jobs. The slide shop were the door slides, and these guys would go out to the airplane. They'd blow the slide and watch it deploy. Then the mechanics would help drag it into the slide shop. They do a full inspection, do a test to make sure it holds pressure for a certain period of time, and then repack it, whatever they do, routine time scheduled maintenance on the slides. But it was carpeted in there because the slides had to sit on the ground. It was air conditioned. They had a radio. It was a sweet job. You wouldn't learn anything about airplanes. That would be the part that would suck. Is you'd only learn slides. But when you're in a part of the country where the weather is crappy, I can tell you there's lots of nights where I was miserable. It was either hot or freezing. I've changed parts on the bottom of an engine where the cold rainwater is running down my arms. I'm literally tying rags to my wrists, trying to get that water to run down the rag instead of my elbow and into my armpits and down into my clothes. But
You need a dry suit.
yeah, I mean, you show up at work, just thinking, just like a day like any other day. Then it's raining, or they move you. because the guy who happened to notice that it was raining called in sick because he didn't want water running down his arms. You think that doesn't happen? Okay, so like I was saying, don't get caught up in the 0.5%, the 0.25, 0.1. The only ones you'll be asked are like orange, where the number is 3 and it's 3%. And I think there's only 1 and 2 between now and the end. If you get them wrong, you know, you lose a point and it's not going to make much of a difference. But there's an example, red, black, and brown. So red is 2, black and black are your 2 zeros. That's the one I got. And it's 0.7%. Actually, I did get it right here. It's 0.1%. So my mistake. Confusing that.
So would that be the most expensive?
That would be a more expensive. These aren't particularly expensive parts. But when I say expensive, I say that because gold is, when I was studying resistors, it was gold and silver and no stripes. And as I recall, that was the only resistors they had because we didn't have electronics like we have today. So when I say more expensive, I try to get you to remember gold being a more accurate, more expensive. So this is 0.1%. So this is a very accurate resistor. This is a result of technology and that need as to whatever this is placed in. So yeah, if you were to buy this, it would be a much more expensive part, but not overly expensive. I don't know what these things are. When they're mass produced, it might be 8 to 12 cents a piece, I'm guessing.
So what, when you're breaking that down, why, your third color, does that still determine the number of zeros? Or does
It doesn't. When you've got 4 color bands,
Yeah,
your last band before there's a gap here.
yeah.
So that gap is one of your clues. That it's the last band is your multiplier.
Oh.
So and in this class we don't have too many examples of this. The most pretty much all the ones I'm going to test you on are 3 bands without the 4th. But they behave the same as long as the last band before this gap, that's going to be your multiplier, meaning that's the number of zeros you get. So these are ceramic resistors. These are going to take a higher current. In many cases, they're going to put the resistance right on them. Let's see. These are watts. That's a 1K. I'm not sure exactly how these read. That's 10 watts. I'm not sure. I don't know. Actually, this one looks legible. It looks like 39. That might be a 39K plus or minus 5%. And it could be that the value is on another side. The example of this picture I took was to show you the wattage at a higher current. These resistors get warm because they are creating resistance. And this is a ceramic resistor, so it will withstand a much higher heat. That was the point of that picture. And there's another resistor. How good are you guys at soldering? Obviously, you'd never solder that one. That's placed by a robot or machine. But that's how small resistors can be. So we talked about Ohm's law. That's all I got for that. This class officially ends at, I don't have it right here.
7:50.
Okay, so we're an hour ahead.
6:30.
6:30.
Yeah, I got plenty to cover.
Much more videos.
Videos are great.
Next is what? Series?
I want to show you a little bit about, I'm trying to think of what I can show you. let me show you a couple of series circuits again to get that fresh in your memory. Maybe I'll make it a little tougher. And then maybe I'll throw in a parallel and we'll start to look at some of those, how we figure out parallel resistance. So typically when I have a schematic, I'm going to ask for, this may not be in order, resistance total, current total, voltage, which is E for R1, and sometimes you'll get them all. Voltage for R2 and voltage for R3. And I could also do power total. So let's go with larger aircraft are 24 volts. Why do I say 36? 36 is sticking in my head for some reason. 24 volts. I'm going to do it like this. Put 3 resistors in here. I'm going to go 1500 ohms, 720 ohms, and let's go 275 ohms. And then so I'm going to make that 24 volts. I didn't put voltage total because I pretty much gave you that answer. So do you guys remember enough from last week to tell me? You can actually figure out all of this information.
So you can add the resistors on.
I'm going to add the resistors first.
So the first you need to figure out the resistance, right?
Yeah. Resistance total. So they're in series. What do I do with resistance in series?
Add it all up.
It's cumulative. If you remember my example of the turnstiles, suppose it takes us 10 minutes to get through the first turnstile, but there's one behind it that takes us 15 minutes, and another one that takes us 5 minutes. If we're in series, it's going to take us a half hour to get through all those turnstiles, right? So resistance and a turnstile would be an example of something that's going to create us to slow down a resistance. So when our resistors are in series, we add them up.
So 25, 25.
2,520? 485. 2495 ohms. Get in the habit of putting the symbol. Because when you write that, you go, okay, that was resistance. You do tend to double check. So my resistance is, I have a voltage and I have a resistance total. So I can figure my current total. Do we get it yet? Okay, so I'm looking for current, so I'm going to block current and I'm going to divide volts by resistance. 24 divided by
0.0096.
and that is amps. So now I'm masking the voltage drops for all of my resistors. Remember how to do that? Yep. If I want voltage, current times resistance. So that 0.0096 current is the current for which resistor? All of them, thank you. The current, whatever flows current is flow, whatever flows through here has to flow through everything. So all of these campsites see the same amount of flow.
So is it, do you say that's,
So what are the current of 0.0096?
times one of the, resistor one?
14.4.
Did you give me an answer or are you asking me a
But no,
question?
if you got the 1500.
14.25?
14.
14.43.
14.4.
So that's most of it. Or that's about half of it, I guess. Close. No.
Sorry, what did you guys do? I kind of missed something.
Okay, so my current, we got, you know how we got the current?
Yes, we got that.
And you know the current is the same for all the resistors. Because whatever flows, that's flow. So each of these resistors. Now if I want voltage for each of those, I have to use whatever this resistor sees. So this resistor sees 1500 ohms and it also sees a current of 0.0096. So to get voltage, I have to multiply current times resistance.
So it's 1500 times.
1500 times 0.0096.
Okay.
And if you do that one, you should get 14.43.
And you're gonna get your voltage for that, right?
Now, and then for resistor 2, I'm going to multiply 0.0096 times 720.
6.912.
6.912. I'm not using different colors for any reason. Just whatever I happen to grab. That's volts. So now I'm going to multiply the current
275.
times 275.
2.64.
2.64 volts. Now, when I get to this point, I'm going to add these up just to double check my work. And what will I get?
Should get
Yep.
24.
If I add these two voltages, I should get 24 volts, or pretty darn close.
Oh my goodness. This is like magic.
That's Kirchhoff's law.
It's going to 0.
If you get anything other than exactly 24 volts, it's because of this rounding. You know, this 0.0096, it may have gone further down, or the voltage may have gone, but it's just rounding.
About by like 0.016.
Yeah, if you hadn't rounded any of these numbers, they would have come out to 24. So that's how one way to check your work. If you had gotten anything other than 24 volts, one or all of these numbers would have been wrong. Or maybe even your current might have been wrong.
So you're saying the total power would be the current times
Okay,
the total
Power is watts.
watts.
So now to get power, it would be total current times total volts will give me total power. So when I use current, I'll use the one current they all see, and I'll use the 24 volts.
For testing purposes, you'll take the 23.982.
You know what, for me, I would, since I gave you the 24 volts, I would use 24 volts.
No, but testing purposes, will you take the 23.982?
Oh, yeah. Oh, I can tell. I mean, rounding, you're gonna be, for this final number, I mean, if you were figuring there's gonna be times when I don't give you this voltage right here. There's gonna be times when I'll give you the current, and I'll give you the other values, and you'll have to. I'll give you the current and the resistance, and that's it. With current resistance, you can figure each of the voltage drops, and you can tell me what that is. Yes.
So your power total is at 0.2304 amps.
That's what I
Point 2034,
23.
and it's going to be watts.
0.23.
Is that the ultimate?
0.23?
Is that the ultimate outcome? Is to
2304.
have a appliance that needs you're just trying to essentially get to the correct power, right?
You are, well, what I'm trying to do is I'm trying to teach you Ohm's law so you see how all of these work.
Right.
Now you've got a water heater, so if you buy a new water heater for that trailer you're working on, it's going to tell you that it's so many watts.
Right.
And then you know that your power supply is 120 volts. So now you can very quickly learn about what type of breaker. Or if you have a breaker already in the trailer, you know that you can do suppose you have a 15 amp breaker. and you've got 120 volts. Somebody tell me watts. 120 volts, 15 amps.
Oh, that would be 120 times 15.
Yep, 120 times 15.
1800 watts.
Okay, 1800 watts. So in order for me to run anything without breaking that, blowing that circuit breaker, it's gonna have to be less than 1800 watts.
So that's the ultimate goal, is to run an appliance with when they tell you the power, and this tells you.
You're gonna be able to figure out lots of things.
Right.
Once you figure out the power or the current, like the power, watts is an example. If I'm running batteries, or batteries are measured in amp hours. I might have a battery that's 750 amp hours. So if I have if I'm listening to the stereo in the car and it only draws an amp, technically I should be able to listen to that for 750 hours.
Yeah.
If the stereo takes 2 amps, you can cut the 750 in half. So what I'm teaching are all the relations. I mean, I'm not teaching you any one thing. There's a lot of different things. I can tell how long a battery is going to last. I can tell what type of circuit breaker I will need to power something. I can determine if I have a circuit breaker, how much I can put on it. I think I said 1800. So if I get a hot water heater that is exactly 1800, I'm probably taking a risk of being right at the edge where that breaker is going to blow on me occasionally. And if that's the case, I definitely can't plug anything else into that area, because that water heater is going to probably plug into an outlet. If it's a little one like you're thinking, you can't. That outlet maybe daisy chained to a few others. So I would go with less. Yeah, I just did my kitchen, so I figured I looked at the wattage on my coffee maker and my toaster oven because they were going to be on one wall, and I figured the wattages, and so I had to move. I had to run separate. Plus, I had a fan over my stove, and they were all together. So then I had to figure out, can I run those on one 15 amp breaker, or do I need to separate them to different breakers? You're not necessarily going to be rebuilding a kitchen, but you're going to find that when you have loads, this stuff's going to come to mind. We'll continue to see examples. I can do another one like this if you want.
Let's do it.
Question, yes?
When we get the power total, you get the resistance and voltage, right?
To get power, I did current times voltage.
Yeah, but when you want the voltage 24.
Okay, well, this one, when we did this example, it was this one here was 24 volts. So we got 0.2. That looks awfully small.
0.2304.
0.04.
Yeah, 0.2330.
0.2304.
Yeah, but
That's it.
do you multiply by 24 or 23.9?
Okay, what I had is, this is power total. So I'm going to use voltage total.
So you
Now I can figure the wattage for each of these. If I wanted to know the wattage for this one, I would use, this is R3, I would use 2.64 volts. Because this resistor sees it's functioning off of this much voltage. That's the voltage that relates to R3. So I can figure the watts or the power from just this one resistor.
Yeah, I understand this part. Voltage, do I get the total that I got, the 23.9, or do I use?
Oh, the 23 point, I gave you this number. I put it on the board, so I would use 24. The 23.9 you got was an error based on rounding. You could, and the answer is still going to be close enough that I'm going to know that the math is correct. If your math is correct, you're not even going to be close. It's going to be way off. I mean, we've got decimals. This is 0.2304. If you had this wrong, you might have a 9 out here, and I know, it's just because you do the wrong process. It's going to be way off. If you're close, I'm going to know you did it right, and that's what matters. I'm gonna go 12 volts. So I'm gonna go 75 ohms. I'm trying to keep the numbers simple. 110 ohms. 65 ohms. With that information, you should be able to give me all of this. Did we get a resistance total yet? 250 ohms. So now I can get current with my resistance. 0.048 amps. Now I have a current, and that current is series circuit. So that current is the same for all of those resistors. Each resistor sees that same current.
First one's a 3.6.
Okay, R2. 5.3. 5.3 volts. And that should be 65. That's going to be its lower. The voltage should be a little less. So what's R3?
2.1.
2.1?
3.
3.1.
3.12.
3.12? Now, me, I'd add them up. It's just a habit to make sure that I get my original 12 volts or close to it.
Would we round up with these or
no? Normally, what I do when I do this stuff, I try not to round too much here until I mean, as I'm doing the math, I'll round off on my final answers. But as I'm doing the other math, until pretty much I'm done, I don't do much rounding.
Okay.
Because if I round and round and round all the way through, it just gets further.
I was making sure because I got 5.28.
Okay, 5.28, and that's fine. So somebody probably gave me rounded.
Alright, that's alright, let's make sure it's alright.
Yeah. It's
They're all
Yeah, I got the same.
so did everybody add them up? Add the 3 voltages, and you should pretty much come to 12 volts, give or take a small fraction.
Yeah, well, 5.2 is
Okay. So that was probably closer to 5.28. Either I would accept either is correct. I would accept either answer is correct.
Resistor.
Yeah, exactly. By the R1, R2.
Okay. I want to do another one, but next time I'm going to give you current and resistance, but I'm not going to give you the voltage total. You can do power if you want.
On the resistance, you're looking for the voltage drop. Is that technically how you word it?
This for each resistor will see a voltage drop. So these values are voltage drops.
Okay, that's a.
And Kirchhoff's law says as we go through a series circuit, each voltage drop will add up to our original source voltage. Okay, I'm ready to start erasing. Ready to move on? Going, too late.
I times B. So I times B.
Contrast up here. 275 ohms. I'm gonna make that 350 ohms. And 60 ohms. And I'm gonna erase this current total And I'm gonna ask for voltage total. And I'm gonna give you a current. So I'm gonna put this next to the battery because this is gonna represent my total current. A 0.035 amps. So now you should be able to fill out all this information.
So.
Okay, how are we doing? And what's our resistance total?
665.
665 ohms. So now, anyone come up with our voltage yet? Total?
Yeah, for volts. Or for just like.
That's going to be the last thing you're going to get. But you could get that right off the bat.
23.275.
Yeah, that's what I got too.
I got 685.
23 points.
275.
Oh, it's 2K.
So that's what.
Now, if you now, there's a couple things. If you notice with the current, right off the bat, you can start doing and getting all your voltage drops and add them up. But if you take the resistance total and do the same problem, it'll give you the voltage drop or the total voltage without having to add each one up.
Say that again?
Okay, remember how we got the resistance of each, with the current, we got the voltage drop of each one. So real quick, since I'm here, what are the voltage drops for what's the voltage drop for R1?
8.925.
8.925 volts. And what's the next one?
12.25.
12.25 volts, and the last one?
2.1.
2.1 volts. Now I can add up these three voltages and get my total voltage, or what I can do also is I can just add up the resistance total, which is 665, and multiply total current times total resistance, and that'll give me total volts. So I could just take the multiply these two together. Resistance and current. Resistance total. Oh, I'm sorry. Resistance. Yeah, this one, these two. Sorry, I had current there and I just didn't get out of my head.
So in a case like that, you're not gonna say it's 24 volts. You're gonna say it's 23.275.
You know, I would say 23. I made that up out of my head. So I would say that's 23.3 volts. But you see what I did is I can do each resistance separately, or I can add the resistances together. I know I may have lost some.
You take
Okay,
this one.
do you see how we got each volt? Did you see how we got each voltage drop?
Yeah, so you add
I
the plate
just-
resistance,
Or
got
you
that,
just put,
and
you
then
just
took
added
the
it up there
665
because that.
That's
and
your-
times
that's your-
0.035 amps.
Yeah, it's your current.
And that gave me,
I guess
since this is the resistance total, this is all the resistors combined.
I got that.
So with all the resistance combined times the current, that gave me the total voltage.
So amps and currents are the same thing.
So, yeah, current is amps.
Okay, so. Yeah, that's what I was- yeah, I got
So
Resistance and all.
I got, when I did 255 times 0.035, I got 8.925 volts. So basically,
it.
it's,
So it's the same as your previous question, instead of just B, it was A, and that's where I got lost on.
This one.
Right?
yes, but this was volts.
It's volts.
Actually, no, the first one was current. I had current here. See this amps? This is, right here, this is I total. All the previous two problems, I gave you voltage. I gave you the voltage, and you had to figure out the current. This one, I gave you the current, and you had to figure out the voltage.
Okay, so it's actually supposed to be.
No, that was.
If it's hard, we'll do more.
No, I feel like just with more practice, I'd get it. But I'm the only one who thinks it's hard. So
Now,
don't.
and it is. This has got to be daunting, and there may be people who are just totally lost. But you have 4 values. You have current, you have resistance, you have volts, and you have power. If you have any 2 of those, you can get the other 4. So you have,
I think for me it's just because it's not what it is. Like
Okay.
R is not.
the other day I gave you a grid, and I've been working without it. This is R1, R2, R3, and then total, and then P, R, R, V. That's done.
You just saw it at the top.
Yeah, that column is.
Oh, there you go, yeah.
Arrow.
Was that
And this, I was kind of shortcutting just doing this, because it was fairly simple. I at least, maybe it's not as simple because we're learning this. Okay, when I first gave you, this is the information I gave you. I gave you total current, 0.035 amps. I'm writing in red the stuff that I gave you. 255 ohms, 350 ohms, and 60 ohms. So this was the information I gave you. When I have a grid like this, anytime I have 2 values in any row horizontally, I can figure out the rest. But I don't have 2 values in any of those, do I? I do if you consider the current, it's a series circuit. This value is going to be in each of these 3.
So, I got a quick question on this last one. What's your power curve?
The power total,
That's your
It's gonna be
0.035
total
times-
current times total voltage is going to give me total power. So multiplying these 2 together will give me this number.
Not the resistance, but the
No,
point
because
zero
that's
three five.
0.035.
Volts and current. Volts.
volts
Oh,
and
yeah, I'm
current.
sorry. I did it again. Multiplying these 2 together,
No.
No, the.
Times only
current,
3.075.
multiplying these 2 together.
Yeah.
I do that on purpose to make you think.
And then you can
But it
do
just confuses people
Yeah,
that
yeah.
don't get it.
which is still power.
Make it sure.
3.14.
Just hit
So
that
with
triangle
that-
down.
Yeah. What is that? What is that?
No, not in parallel.
Hey, that-
I'm really trying to grill into a series right now. Okay, this is where I keep grilling in that the current, when I give you total current, okay, here's what I could have really thrown you.
That current is consistent all of this, right? Okay, so you put.
Okay, suppose right here,
Exactly.
I told you next, when I put a value next to the,
So it's altered.
I don't remember what that value was.
0.035 amps.
0.035.
Thank you.
I had it in my mind.
Okay, when I put a value here next to the battery, that's total. That's this column. Those are totals. So there's going to be a time when I'll put ohms here and nothing else. And if I put it next to the battery, that's total. That's my total row down here. So suppose I did this. I gave you resistance for these three, but I gave you the current for R1.
So
They're all the same. And I'm going to do that to you. So right now here, I didn't give you a total, but I gave you 0.035 amps for R1. But since it's a series circuit, they're all the same. So now I have two values here and here and here. I can add these together and get my 665. It's supposed to be in ohms, not quite an R. Made it worse.
So you have your current, you have your resistance, and then you get your voltage from that, right?
Well, I have 0.035 in all of these, so I have current and resistance, which will give me volts. So I can literally multiply these two together and get this. I can multiply each of these, and we did those. We got 8.925. And R2 gave us 12.25. And the last one gave us 2.1. So what I can do, you could have done either. You could have gotten these three voltages separately and added them for your total, or you could have taken your current and your total resistance and got that value, which is 23.275. It's probably going to be easier for you to do the grid each time, because what you need is two values or more horizontally. It doesn't matter if the circuit is parallel or series parallel. Once you do this grid horizontally, you can do just the regular formula, and you can fill in the other blocks.
Is on the left side, is it always going to be with the resistance?
The left
variables, same variables all the time, or the only resistance on the left for that chart? Is it always going to be resistance, or?
I think, well, yeah, usually what I'll do on this side of the grid, you can do the grid any way you want. You can put the resistance up here. I'm doing it this way just to keep it uniform. But yeah, I usually do the resistance down the side in total. When everybody with me?
On the watts, you can find the watts per resistance.
Yes, the watts I didn't fill in because it's just basic math. Power, volts times current. So right here, volts times current. I multiply these two and I get that all the way down.
Parallel circuits?
We can do parallel. Parallel though, the current is not the same in parallel.
Could you do an example of parallel?
I can, and I want to. I'm itching to.
Can you show us one?
But I want to make sure that
Show us one.
I want to make sure that you have somewhat of a good idea of how this works.
What is this bit?
July 6th.
I can give it to you now.
July 6th.
I'm not going to quiz you on this for a little while. It'll be at least a week or two.
I forget in a week.
But this, what we're doing here is pretty much 90% of this course. It gets tricky. I mean, it's hopefully you'll see it as like a maze or a puzzle.
I guess we're opening questions right now.
Yeah.
So on the test itself, is that going to be going over terminology, or is this going to? I'll wait. The test is it going to be over terminology because there's quite a bit of information in the reading. And You still have yet to go over the different stuff.
The I can show you a test. I can show you. I have a sample version of the midterm if you just want to see.
Yeah, I mean, help us know what kind of questions you're gonna be asking us, because you go through 5-6 pages of this, there's a mile of information
There will be.
without practicing.
I'm not gonna test you on anything we haven't talked about, and I'm gonna remind you and show you all the way through.
Would you just give us one quick example of a parallel before you jump in?
And I keep my charger plugged in because my computer, although the battery isn't too bad, it won't give me much of a warning. I can figure out with all this, if I'm looking at a computer, on the label it'll tell you how many watts that computer uses. And if you look at the battery capacity and use these values, you can determine how long you can expect your battery, your laptop to last on a charge. And this is you can use this for a lot of different things around the house or for whatever reasons. Okay, so let's give you a parallel now. I think you're probably gonna hate me, but
I'm not writing it.
Now, in that sheet I gave you on the first day, when I start entering the resistances in here, in a parallel circuit, I cannot add them down. They will not add. The voltages in a parallel circuit, if I give you, in a parallel circuit, if I give you one voltage, I've given you them all. It's kind of like current over here. In a parallel circuit, all the voltages are the same, and I'll show you why in a diagram if you don't remember me drawing.
Isn't that why they run houses in parallel?
There are, let's see, there is, I think the parallel is mainly because it's AC. You've got when I come into the power that comes into the house is going both directions. And as I come into my outlets, these two can't cross. So I don't know if I'm giving you good information or not. Actually, this would have come over here. If I draw a line, suppose this is a wire, and I have another wire. I'm going to do it in red just for clarification. You're going to know it's a different wire because it's red. But if they're the same color, what I do is I draw it this way. So where you will see things that look like this, that look peculiar, but when you see that, that's like a little bridge. They don't touch. If these were intended to touch, there would be a node like that, a little dot, and it wouldn't have the bump in it. It'd be straight. So it would look more like this. That would be a direct indication that those shared. AC, you can't daisy chain, you can't string a house in, well, I guess you can. But remember you were asking why they do houses parallel. Remember how much trouble we've had with Christmas lights.
Yeah, you take one out.
That's series. Yeah, that's series. If you wire a house in series and something fails, you've lost everything. Not only that, but it wouldn't work unless you had something plugged into it. The moment I took my alarm clock out, I break the circuit and everything else downstream of it and upstream is.
That's a good way of explaining volts, right? If you take one of the
It's more like
power switches out, they're all going to continue to have power.
That would be more of an explanation of current flow. If I create a break, then the flow stops.
It says here that appliances are connected in a home in parallel so they can all be turned on and off individually.
Yes, on and off individually. Because if they were in series and I turned one off, they'd all go off. Okay, so,
Who needs brain when you have Google?
I'll have no Google during the test. Okay, so I have a 12 volt supply. Here's my first, I'm gonna make 2 resistors. Okay, those 2 resistors are parallel. I'm gonna keep it simple, I'm gonna make them 10 ohms and 10 ohms. So now if you notice, if I have we'll pretend that's black, these are my leads to my meter. If I put the red on the positive side, the black on the negative right here, I'm getting 12 volts. If I put it here, 12 volts. Put it there, 12 volts. So in this example, the voltage drop for R1 and R2 is 12 volts, 12 volts, 12 volts. They do not add up. It's like current. So parallelism is different. This is something, like I said, when in current in series is the same all the way through. In parallel, voltage is the same all the way through. And you have to remember those. We're doing somewhat of a puzzle, and if you get, or a maze, however you want to visualize this, if you get it wrong in all the numbers and values, remember how we were getting some of these values, we use them in math problems later. If you goof that up. We have, in your test, when I do this, 1, 2, 3, 4, 5, this might be one problem, but it's 6 points. You mess up resistance total, you add it wrong, every number down here is going to be wrong. So you didn't miss 1, but you just lost 6 points off of a test that may be 30 points. So again, current is the same all the way through in series. Volts is all the way the same in parallel. For that reason, when I put my meter here, I'm still on the same wire that I'm attached to my battery. Each of these sees that 12 volts. Now, and I haven't forgot to show you, I'll show you a midterm sample. And I have this open to the page. You guys were all supposed to have a certain amount of math to have this class. For in the book, this is a lot more complicated than it has to be. And I know that it's true math, but I kind of butchered it a little bit. Let's go. What it is it's I've got 10 ohms. So it's 10 over 1 plus 10 over 1. So 10 over 1 is 10, right? Mm-hmm. So when I put a 1 over it, I haven't changed anything. What I have to do is divide 1 into 10, and then I can add it. Let's see. Anyone do this type of math before?
I was 1 over 10.
Are we trying to find the?
I've done it. It's easier for me. I haven't taught this since last semester. And I can do it. I'm trying from memory, but I usually have my crutch as my slide.
So I have a question.
I'm trying. Let me instead of making
It's 10 and 1/10.
I know it is. Let me. Let's see. Does that change it? 1 divided 50. Okay, no, it doesn't change it. Let me find it. There's when we do this. Does anyone not have a scientific calculator? I'm going to teach you both ways.
It's, yeah,
And we go now? It's like 10.
are we solving for the resistance?
Okay. So the book. This is the way the book shows it. Page 10-41, if you have your book, this would be resistance total equals 1 over R1
Yeah, there we go. That's straight up.
plus 1 over R2. And then plus R3 plus R4.
So we're gonna have 1 over 10 plus 1 over 10. Right?
Yes.
So then it's, since we have a common denominator, so that's 2 over 10 over 5. So you have, what is that, 1
Usually I teach this to the point where everybody understands it, and then we go to our scientific calculator. But give me just a moment.
It's 1 over 1 10. So if you guys can reduce it, so it's 1 over.
Okay, so
1 over 1/5, yeah. So 1 divided by 1 over 1/5.
so it's 0.2 plus 0.2, or the total is 0.2.
Yeah, so I got 1 over 10 plus 1 over 10 is 0.2, but then if you do that 1 over, it comes up to 5, right?
Yes, and it should.
And that's what it should be, it's 5, half.
Yeah, so you got 0.2.
Yeah, so that exactly, that number down there is 0.2, then you do a 1 over, do that 1 over, and then that's 5.
Okay. And it's 1 over 0.2.
Yeah.
So you got the
That's
this was
0.1 plus
0.1.
0.1, yeah.
So this actually down here becomes 1 over 0.1
What?
plus 1 over 0.1 equals 1 over 0.2.
Which equals 5.
And 1 over, so we invert it, right?
Yeah.
So we put 0.2 over 1?
No, I just, when you invert 1 over 0.2, it's 5, which is exactly what, if you have in parallel, like 10 and 10, then you're.
So 1 over 0.2 equals 5.
Yeah, and you were looking for 5 ohms.
Let's see. I think if it was 30, 35,
Oh, I see.
25,
You did that a little different.
17. I'm just doing this from my head. We invert it. I think this becomes, if I had 35 ohms, 25 ohms is 17 ohms, and we'll figure that out in a second. We invert. So this becomes 3, just bear with me for a second, 3 over, this may not be right, but I want to see if it comes out, 50, 60, 77. What's, it's 3 divided by 77?